In December 2024, just before Christmas, Parker's solar probe fell toward the sun faster than any machine humans have ever built, about 430,000 miles per hour. At closest approach, it passed roughly 3.8 million miles above the solar surface, inside the sun's outer atmosphere, the corona. Then, for days, silence. No live signal, no rescue possible. Finally, a tiny tone returned from deep space. Parker survived. And that matters, because the sun is not distant. It is touching our planet every second. The sun is not a ball of fire. Fire needs oxygen. The sun is plasma, charged gas shaped by gravity, fusion, and magnetic fields. It is about 109 times wider than Earth, and more than 1 million Earths could fit inside it. In its core, hydrogen fuses into helium and releases energy. That energy can take many thousands of years to fight outward through the sun. But once light escapes the surface, it crosses 150 million kilometers of space in about 8 minutes. Ancient energy, arriving as daylight on your skin. Every sunrise carries this long journey. But this star is never still. In September 2013, a magnetic rope of solar material erupted and tore through the corona. NASA called the glowing path it left behind a canyon of fire. It stretched about 200,000 miles, roughly 25 Earth's end to end. From here, it looks slow and graceful. On the sun, it is violence in disguise. The bright ribbons are not flames. They are plasma and invisible magnetic fields rearranging a star in real time. Sometimes the plasma does not escape into space. It rises, cools, condenses, and falls back along magnetic field lines, like rain following invisible rails. Scientists call it coronal rain. NASA's Solar Dynamics Observatory watched this happen after a 2012 eruption. The strange part is the place it falls through, the corona, an atmosphere that can reach millions of degrees, far hotter than the visible surface below. That backward-sounding mystery is the coronal heating problem. It is beautiful, but it is also a map of magnetism. This close, the sun stops looking smooth. Each glittering cell is not a spark. It is a restless structure larger than a city. When magnetic fields twist, stretch, and reconnect, the release can become a solar flare. The strongest class is X-class. A flare's radiation reaches Earth at light speed, about 8 minutes, so the first warning is often the event itself. It can black out high-frequency radio on the sunlit side of Earth and distort navigation signals. In May 2024, active region 3664 5 major flares, including an X8.7 blast. In October, region 3842 produced an even stronger X9.0 flare. The message was simple: solar cycle 25 was not quiet. Those are not movie numbers, they are operational warning times. But a flare is the flash. The heavier punch is a coronal mass ejection, a moving cloud of magnetized plasma. A large CME can carry billions of tons of material into space. The danger is not that it burns Earth. Space is too vast for that story. The danger is magnetic. If the cloud's magnetic field points the wrong way, it can pour energy into Earth's magnetic shield and start a geomagnetic storm. The warning story is 1859. During the Carrington Event, a powerful solar eruption struck Earth's magnetic field. Telegraph systems, the Victorian internet of the day, sparked, shocked operators, and in some places kept sending signals even after batteries were disconnected. Auroras appeared far from the poles. It was beautiful, and it was a warning. In 1859, that warning hit a world without GPS, global satellites, aviation networks, or continent-wide power grids. The grid of that world was simple. Now imagine a Carrington-scale storm aimed at today's technology. Long power lines can behave like antennas. Geomagnetically induced currents can overheat transformers and trip protection systems. Satellites can struggle with charging, orientation, tracking, and extra atmospheric drag. GPS timing can become unreliable. Flights may shift routes when radiation and communication risks rise near polar regions. Not every city would go dark. Not every satellite would fail. The realistic danger is more complicated, small failures spreading through systems that depend on each other until modern life starts losing its rhythm. A hospital, airport, phone tower, and satellite clock can all depend on the same hidden timing web. This is not science fiction. On May 10, 2024, Earth was hit by the Gannon storm, the first G5 geomagnetic storm in more than 20 years. It did not cause global catastrophe, and that is important to say. But it did trip some high-voltage lines, overheat transformers, push GPS-guided tractors off course, reroute transatlantic flights, and increase drag on thousands of satellites. NASA later called it one of the best documented geomagnetic storms in history. It proved the point quietly: our technology is not above nature. It is wired into it. The hopeful part is that we are not blind. Space weather centers watch the sun constantly. NOAA's DSCOVR spacecraft sits near the L1 point, about 1 million miles from Earth, tasting the solar wind before it reaches us. That usually gives only 15 to 60 minutes of final warning when a CME is almost here. Parker Solar Probe helps earlier in the chain by measuring the corona and solar wind where the storm begins. We are learning fast, but prediction is not the same as protection. That gap is where preparation matters. Look at these auroras. They are Earth's defense system made visible. Particles from the sun are being guided by our magnetic field and lighting the upper atmosphere. The same process that paints the sky can test the machines below it. The sun gives us life, warmth, weather, and light, and sometimes a reminder that Earth lives inside Earth's reach. So here is the question: if we had 1 hour before a Carrington-class storm arrived, would we really be ready?